Still in chapter 12, we're going to talk about rolling energy and static equilibrium. These are still all part of the chapter 12. Rolling energy says that if you have an object like a ball or a disc and it's rolling along the floor or whatever you want it to be, it has energy, but it has two kinds of energy. It has kinetic energy, but it has kinetic energy of translation because it's moving forward, which is called 1/2 mv squared. We already know that. That's the energy of the translation or the motion. And we measure the velocity as the velocity of the center or the rotation point as it moves forward. When we say the velocity, you're doing the velocity of the center of the object spinning. You don't measure it on the edges because those are not going to be the same. Because not only is it moving forward, but it's rotating at the same time. So when you're rolling an object, it has two forms of energy. It has translation and it has kinetic energy of rotation, which is equal to 1/2 I omega squared. Okay? So if you have an object that's rolling down the floor, let's say we have a disc. Okay? And we have a disc and we're going to roll it down a incline of some height h. We want to know when it's down here, what is its velocity, as an example. Well, this is an energy problem. Initial energy is equal to final energy. But the initial energy is the height of it. Remember, the height is now always to the center of mass. And that's just going to be mgh. But down here, we used to say it was just kinetic energy, but we can't say that. Well, it is just kinetic, but it's not just kinetic of translation. It's kinetic of translation and rotation. So you have to make sure that if something is rolling, you have 1/2 mv squared plus 1/2 I omega squared. So it has energy of translation and energy of rotation. That is why an object that's sliding on a frictionless surface is always faster than one that's rolling, because the rolling energy takes some of the energy. So its velocity isn't as in the forward direction, is not as fast. All right, let's solve this for v squared. You say, oh, but v squared is going to be difficult because we have omega squared here. So we're going to have to convert this. Remember, omega is equal to v over r. We usually write it as v is equal to omega r, but if I rotate it, omega is equal to v over r. So I'm going to expand this. mgh is equal to 1/2 mv squared plus 1/2. Remember, I for a disk is equal to 1/2 mr squared. That's what I is for a disk. We looked that up in our table. Omega squared is just going to be equal to v squared over r squared. Notice that these r squareds actually cancel out. When those cancel out, then we have that mgh is equal to 1/2. Actually, we can cancel out all the m's too, just to make life easier here. So gh is equal to 1/2 v squared plus 1/2 times 1/2 is 1/4. All that cancels out and we're left with just v squared. Or we can say that gh is equal to v squared times 1/2 plus 1/4. Or gh is equal to v squared times 3/4. Or v squared is equal to 4gh over 3. Or v is equal to the square root of 4gh over 3. All right, so the only thing that matters with how fast it's going is how high it is, which is exactly the way it was before when we just converted from mgh to 1/2 mv squared. Okay. So what that means is some of that energy went directly into rotating as well as going down. If it wasn't rotating, let's say it was just going down, sliding on a frictionless surface, then remember mgh is equal to just 1/2 mv squared. The m's cancel and you get v is equal to the square root of 2gh. This velocity is definitely higher than this one. This is 2 times gh, this is 4 over 3 or 1.33 times gh. So an object that's sliding on a frictionless surface will always be faster than one that's rolling. All right, let's talk about static equilibrium. In static equilibrium, this is a very important topic. In fact, it's so important for engineering. If you're doing construction engineering, you have a whole class in it. They call it statics. The idea is if you build a building, a bridge, anything, any kind of structure that's not moving, then that's static. And so when it's static, all the forces and all the torques have to be set to 0 because there can be no acceleration either in the x direction, y direction, z direction, and there can be no rotation about any axis. And that's what engineers do, especially construction engineers, when they have a plan to build a building. They say, okay, I have to look at all forces that could be involved and make sure that the structure can withstand all that and stay as a static structure. So for static equilibrium, what we do is we have to create a situation where net x is 0, net y is 0, and the net torque is equal to 0. And if you had a z direction, you'd have to have the net z be 0. So this is the first case where when we do problems that have static equilibrium, you have to do an extended free body diagram. For example, let's say we have a block here that's, let's make it like a sign. So here's a wall, and we're going to have a cable here connected to the end of the block. Okay, at some angle theta, and we're going to hang from it. We're going to hang right here. We're going to hang a sign from this bar. Okay. Now what that means is I have to figure out what strength this cable has to be, because I have to figure out what the tension is going to be to hold this bar. And I have to figure out all the forces acting on it. But when we're worried about torque, remember when we did forces, we always just put a free diagram with a dot in the center because that was the center of mass. For net x and net y, that works fine. But for torque, it matters where the force is on the object and where it's going to rotate about. So what we have to do is we have to do what we call extended free body diagrams. So I'm going to draw the bar. I'm going to do a free body diagram of this bar here and put all the forces that are on that bar. And so on this case right here, the tension coming up here, we're going to call this T at an angle theta. Then I have that the bar has mass, so it has a force of gravity, the mass of the bar times gravity, and that's going to be at its center of mass, which is the center of the bar. And then we have this sign, which is also hanging here. This is going to be mass of the sign times gravity, hanging out here at some point wherever it was determined that it was hanging from. But then we also have two more forces from the wall over here. The wall is going to be pushing outward with a normal force, or in this case I'm going to call it a horizontal force, but it's the same as a normal force pushing perpendicular to the wall. Otherwise the bar would go through the wall. But I also have to think about this too. If the bar wasn't connected to the wall over here, the bar would just fall down on this side, right? And it would rotate around this rope. So there is also a vertical force, usually a nail or a screw into the wall or however you connect it to the wall, that's applying a vertical force holding up that end of the bar. So now I have all these forces. I have 5 forces here. We have to set F net x equal to 0, F net y equals 0, and the net torque equals 0. Well, you already know how to do net x and net y, so I'm not going to go over those. But let's look at net torque. Net torque says that this object cannot rotate under these forces. And so what I have to do is I have to choose a rotation point. Now the good thing about this is I can choose a rotation point anywhere I want on this bar. And the easiest place is to always choose the rotation point at the point where you know the least. Meaning we don't know what the vertical force and the horizontal force, the normal force and the vertical force here. So let's call this our rotation point. Then the torque from these two forces is 0 because remember torque is equal to force times the distance times the sine of the angle in between. Well, in this case, the distance from the rotation point is 0, so neither of those have a torque. So it makes it easier. I only have to deal with these 3 forces for the torque. Now, let's say the sine has a length L right here. Then I'm going to look at the torque, and I have to look and say if it's rotating here, the tension is making it go in a counterclockwise direction, so that's positive. So I have the force, which is tension, times the distance, this is FD, distance is L, it's a distance L from the rotation point, times the sine of the angle, in this case our angle is theta. Alright, now we have these two forces, let's do this one first. This is going to be minus, because this force, the force of the bar, gravity acting on the bar, is going to try to make it rotate clockwise. That's a negative. So that's minus mbg. The distance is half of that, L over 2. Right? Now the angle here, though, is 90 degrees, so this becomes sine of 90 degrees. Well, the good thing about the sine of 90 degrees is the sine of 90 degrees is just 1. And then we have minus the mass of the weight, that's supposed to be a W, or sine, I guess that's supposed to be an S. Mass of the sine times G times the distance, which I don't know what that distance is, whatever the problem would tell you. Let's call it X times X times X times the sine of the angle. But again, the angle between this is 90 degrees, so this is equal to 1. And the net torque, then we set that equal to 0. So what we get is that 0 is equal to TL sine theta minus mbg L over 2 minus msg times x, the distance. And then whatever the equation, the problem asks for, sorry, I'm shaking the camera here. Whatever you ask, the equation asks for, you would solve for that. If they ask for the distance that the sine is, or if they ask for the tension, you would solve for that. But this is how you set these problems up. You draw a free body, what we call an extended free body diagram, and then you map out all the torques, depending on whether it goes positive or negative.